Hi ladies and gentlemen, this is Mr. Green and I am once again making a video for AP Statistics. We are on to the next chapter. This one is dealing no longer with normality, but we're going to be looking at bivariate data. Now what does it mean by bivariate data? That means I've got two things that I'm comparing, trying to get some sort of a relationship between. One of the things that's popped up in our school recently is they're trying to compare the relationship between uh, star scores, the Algebra 1 star scores, and the tests that they take, the benchmark tests that they take, and they're trying to see if there's a relationship between those. And I will tell you right now that that's becoming a real live situation that they are actually looking at that. They're trying to say, do those benchmark tests actually predict how well people are going to do on the STAR test? It's an interesting analysis that we're doing. And so it does have real world situations that we're looking at. Two things that don't necessarily go together being compared against each other. And that's what bivariate data has to do. Okay? So that's what it has to deal with. Okay? So suppose we found the age and weight of sample 10 adults, and here's their ages and here's their weight. Well, you know what? We're going to make a plot of this. One of the things I'm going to tell you to do is to turn your diagnostics on. How do you get that on your calculator? You press second calculate. You press a D to go to diagnostics, and you go down here to the diagnostics field, which is down DIG. There it is, diagnostics on, and you press enter on that, and enter again, and it says done. Okay, so we've got our diagnostics on. So we're going to press stat, and we're going to press enter, and we're going to enter this data in. I'm going to go up here and erase this data. Clear. And clear. So you know how to clear data out. So we're going to enter this data in. I got to move my calculator over here to the side so I can see everything, but I'm still just entering the data in. Okay, 24, 30, 41, 28, 50, 46, 49, 35, 20, and 39. And I'm going over to the L2 field here, and I'm going to enter that data: 256, 124, 320, 185, 158, 129, 103, 196, 110, and 130. A little faster than the calculator at entering data in, so it takes a little while for it to catch up to me. Okay, so we've entered this data in. One of the things you can do is you can press a second y equals. You can turn on a stat plot, like this one right here, turn it on, and we're going to come down here and we're going to select this first thing. That is uh, a scatter plot, and that's exactly what they're asking us to do. Okay, so I'm going to just select that one and go down here. Those are all fine values, so we'll just press enter and hit graph. Now it's not going to graph anything because you're not going to see anything there, right? Well, I got to get rid of this here first. Okay, so what I'm going to do is I'm going to press zoom, and I'm going to press I believe it's 9 for statistical plots. And I can't ever remember this, so I always have to look. Yep, there it is, a stat plot. It's number 9. So I press 9. And there's my statistics plot. There is the scatter plot. It just plotted that data out for me. Calculator can be your friend. Okay, so we can produce a scatter plot with this, right? Not a problem. That's what it asked us to do right there. They're asking, is there any relationship between the age and the weight of these adults? Well, if there was a relationship, you would be able to draw a line that would connect them all together. Well, maybe not connect them all, but would be explainable to meet most of their, to explain most of it. Okay? So they're asking, is it a positive, a negative, or a weak, or a strong relationship? Wow, looking at this, it's kind of hard to tell if it's, well, I'm thinking a line might go from here down like this direction, And is that positive or negative? That's negative. Is it weak or strong? Well, you know, geez, these are kind of hard questions to answer, okay? But, here's the data plotted out. Is that the same as my data? Hmm. I don't know what's going on there. I'll have to check that one out later on. But, there's some data plotted out there. Would you say that's a strong or a weak or a positive or negative? Well, the closer the points are in a scatter plot to a straight line, the stronger the relationship. So, what am I talking about? A straight line? Whoops. That wasn't supposed to happen. Let's put that back up here. Thank you. Wow. Didn't expect that to happen. Okay. Pushed the wrong button. Sorry. That's the one I'm wanting. Okay. So if I were to draw a line that went through this data, it might look something like that. Okay? So the closer the points are to that line, the stronger the relationship is. Well, that makes perfect sense. And the further away they are from that line, the weaker the relationship is. So that's how we can get strong and negative. I mean, we've all looked at linear equations before. We know what positive and negative lines are. Well, if it's sloping up to the left, it's a positive relationship. If it's sloping down, it's a negative relationship. I guess there can be no relationship too. If you're looking at the heights of mothers and the heights of their adult daughters, that looks like that might be a positive one. Age of cars in years and its current value, well, it goes down in value unless you're, a collectible car or something like that. So typically it goes down in value, so that would be a negative relationship. The weight of the person and the calories that they're consumed, well, the more calories they're consumed, the weight goes up. Yeah, that's a positive relationship. The height of a person and the person's birth month, yeah, I don't see much of a relationship there. I can see that one wouldn't have any kind of relationship at all. Okay? The number of hours spent on the safety training and the number of accidents that occur, well, yeah, the accidents go down the more people are trained to be safe, right? So you can see how these have a positive and a negative relationship. Okay? Well, there is a correlation coefficient called R. And that's what I had you turn on in your calculators, okay? That diagnostic R. Because what you can do is you can press stat, calc, and do this linear regression number 4 here, or you can do number 8. They're pretty much the same thing. And you press that and you hit calculate, and it actually calculates a linear equation for you. Okay? You can see how it starts with a negative number here? That's telling me that it's a negative relationship. That's what mine on my graph here was saying, was that it was a negative relationship. And this R value at 11, we'll have to look at that. But this R value is a quantitative assessment of the strength and the direction of the linear relationship between bivariate quantitative data. Now, there's a Pearson sample correlation is most used. It's the parameter rho. Its statistic is R, and this is the way it is actually calculated. It's 1 over n minus 1 times the summation of the x sub I minus the x bar. What's the x bar? That's the mean. So xi minus the mean divided by the standard deviation of the x values, and y minus the mean of the y values divided by the standard deviation of the y values. Wow, a lot of work there. Man, just turn on the calculator. Let's see what we get. Okay? That's just the easy way of doing it. Now, we talked about, well, we didn't talk about it, speed limit and accidents, number of accidents. If you look at these two sets of data and you calculate the R, there would be a strong positive linear relationship between speed limit and the average number of accidents in a week. The slower the speed, the fewer the accidents. The higher the speed, the more accidents. That's a strong, linear, positive relationship. Okay? So R is one of these things that has a gives you an indication of what kind of relationship it is. So what we're looking at is an R is going to be between -1 and 1 inclusive. That's what the solid brackets mean. Okay? So if you're looking at it, if it's between 1 and almost to 8, 1 to 8 basically, you would say it's a strong correlation. If you saw it between zero point 0.8 and 0.5, moderate correlation. So I've got both positive and negatives here. Okay? So if it's somewhere in these ranges, you would say it's a moderate correlation. Okay? If it's between zero point 0.5 and approaching 0, then you would say that it has a very weak correlation. And if you go on further, if you get 0 itself, there's no correlation between those two bits of data. None whatsoever. So let's think about that for a second. The value of R does not depend on which of the two variables is labeled as X. You mean I can switch the X and the Y values and get the same R? Let's try that real quickly. See how I got an R of -11 there? Let's try that. Let's just change this and do that again. So I'm going to do a stat calc, and I'm going to come down here and do a number 4, and I'm going to change this from being L1 and L2 to being L2 and L1, and I'm going to come down here and do the correlation, and what do I get? I get the same -11. Completely different numbers up here, but I get that same -11. So it doesn't really, it's not really affected by which one you put first and which one you put second. The correlation will be the same. Why? Because what are we looking at after all? We're looking at a line, and that line is not going to change. Okay? If I change in the x and y's, it might change the line from positive to negative, but it's not going to change the value of that r. Very interesting concept there. The value of R is non-resistant. Outliers will affect the correlation coefficient. It'll affect it tremendously. But if I switch the X and the Y's, that won't affect it. Okay? So, the value of R is a measure of the extent to which X and Y are linearly related. If we took these points right here and related them, and put them on a scatter plot, we get something like this. There's a relationship there, but it's definitely not a linear relationship, is it? And you would get an R value of 0. Okay? This relationship, quadratic. So it's not a linear relationship at all. Okay? So, remember, I'm going to put this final thought up here about correlations and these R values. Correlation does not imply causation. Correlation does not imply causation. You need to keep repeating that. Correlation does not imply causation. You can't say that this was caused by this. All you can say is that there's a strong correlation between the two. And it's going back to that data that I mentioned at the beginning. Okay? The benchmark tests and the star ELC for Algebra 1. Correlation does not imply causation. Where the benchmark test might be a good correlated number to the passing of the star test, it is not a cause of the passing of the benchmark test. And you have to be aware, correlation or a strong predictor does not necessarily mean that it causes the outcome to occur. That's an interesting one. And when we come to Class Connect, we will look at this a little bit stronger, okay? Because I've got some real good data that we'll put together and we'll look at, and I think you will all agree with me. Correlation will not cause. Does not imply that it was caused by the information. So, look for you in Class Connect. And one more slide here. Yeah. Poor statistician here. He's all upset. This guy is saying, he says we ruined his positive correlation between height and weight. Yeah, I can see that one, okay? Not a positive correlation at all at this point. Okay? Remember, lots of different courses. Make certain you're telling me that you're in AP statistics when you send me information, especially K-mails and instant messages. Helps me find your information a little bit quicker. I am available in Toga sessions. If you have questions, please come down to Toga on Monday through Thursday from 3 to 4, and I will be trying my hardest to give you the best answers I can. Okay? I'll look for you next time I see you. Bye.